session is being recorded. Right, the very last window operation process I want to look at is texture recognition. So far we've seen window operators that operate off single pixels, and that gives us intensity shift and intensity multiply, which can be used very effectively for image enhancement. We then looked at two pixel operators, two image pixel operators, single pixel from two images, and that can be used for adding and subtracting images. Not really that important, but it can be used sometimes. We then moved to a window operator, which gave us the low pass filter. Coefficients of a low pass filter are what? 9 of them. Tell him.
-1, -1,
Ah!
-1.
Good attempt, better than nothing. The other one. It's the very simplest window operator of all. It's averaging. So what you do, you take all the pixels and divide by 9. All the weights are 1. So you're just simply adding up the pixels under the window. Then you come to the high pass filter, which is -1, -1, -1, -1, -1, all the way around the edges of the 3x3. Bang in the middle, it is +8. And that will enhance the sharpness of the image. But the disadvantage of that is you lose all the background information. As long as the background is the same value, be it absolute black or absolute white or anything in between, that in the filtered image will go to black. Why? Because -1, 8 of them, +8 adds up to 0. The output will be 0. You can restore the background by adding the original image. You'll lose a bit of the sharpness, but you'll get a bit of a background. So if it's for enhancing and cosmetic purposes, it's better than just having edges on a black background. And then we came to the double window operators, which were the edge detectors. Starting off with the simplest, which was the Roberts. I tend to represent them as a 3x3 window. Go away. But other books will tend to represent them. There is your center pixel, and that, if you like, is A and B. I tend to represent them as a 3x3 window. Output is the center of the pixel, and A would be -1, B would be +1, and all the rest would be noughts. And that is the Roberts. And that is either a horizontal or a vertical edge detector. Which is it detecting, horizontal or vertical?
Vertical.
Vertical, yeah. The horizontal one is going to be +1, -1, and the rest would be naught. So that is V, and that is H. And that is the simplest edge detector. It's crude differentiation, subtracting what came before from what's ahead of the pixel you're looking at. And it's measuring actually the slope of intensity at the pixel level. The better edge detector is the Pruitt, and the Pruitt has weights which take into account the diagonals. And the very best one, and I suspect if it came up in the exam, the one that would be discussed in detail, would be the Sobel. And the Sobel is 2 operators. And for the horizontal, you are looking at the pixels above and below. It could be -1, -2, -1, -2, -1, naught, 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 +1, +2, +1. You look at the values above and below, and any horizontal edge will show up. The vertical one is -1, -2, -1, +1, +2, +1, and the others are zeros. That gives you the vertical and the horizontal edge strength. What do you do then? You've got the vertical strength, the horizontal edge strength. You've got to combine them. You can combine them using right angle triangles, i.e. Pythagoras, which would be the overall edge E strength, edge is going to be h squared plus v squared square root, which is similar to the Euclidean distance. But if you want a quick and faster one, do addition of the modulus. E is equal to mod h plus mod v. And what is the mod of a number? It's the magnitude of a number without the sign. And that will give you your overall edge strength, and that will produce a picture, an edge strength picture. And to locate the edges, you have to apply a threshold to that image, and that is a subjective measurement. Set the threshold that subjectively brings out the best edges. Can't guarantee what threshold it is. If you want a very strong edge, it's going to be a high threshold. If you want a very broad edge, it's going to be a low threshold. Right, so that's where we really were. So that's a summary of so far. I now want to look at texture recognition. Artificial images, industrial images, part sorting and things like that, artificial parts. When you look at the real world, despite all the math finishing here, there are textures you come across. The front of the speaker has a texture. You recognize it as a particular finish. I guess there's texture with a sign there. Texture on those, oh yes, we've got texture on your garments. So the real world, you can't escape textures. And the problem with textures is a texture is a higher order function. I can't specify a texture from a single pixel. The other thing is, if we take a texture, supposing the wall was covered with those dots and whatever, it's very difficult to normalize the texture and fix it in a position, because there's no obvious local features. It's an overall homogeneous feature. If I'm trying to recognize a hand, okay, I can move it so the hand is in up to a vertical position and up to a horizontal position, and so the variation would be restrained there rather than being all over the place. Can't do that with textures. So, if I were to take a texture, let's take, I'll take 4x4 examples. And let's have dot, cross, 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 cross. Now that's a pretty high frequency texture. Lots of changes between black and white. Cross is black, white is obviously white. And if I compared that with a second texture, and here we've got exactly the same number of black pixels. This is very much a low frequency texture. White just going to black. This is a checkerboard, high frequency. And taking a single pixel, can I take a single pixel from this? Yes, I can, I guess. There we're, oh, don't slip down. There's a single pixel, it's black. You can't say anything about the underlying texture. It could have been the first image, it could have been the second image. So we need a multi-pixel operator. And the simplest multi, yes,
Are those dots only in the first?
the notes, yes.
Oh, okay. I see.
Right, binary. And the simplest multi-pixel operator is a 2-pixel operator. And so let's take an operator with 2 pixels. And we're going to use that operator to scan the textures. But we are not, in this case, going to correlate, i.e. multiply coefficients in here with the image. We're not going to do that as we've done with edge detectors. What we're going to do is we are going to record, note, the values under the operator. And this will lead us to a texture co-occurrence you can call it a histogram, it's usually called a spectrum. And this texture co-occurrence spectrum, a bit like the histogram for images, it is a graph of the number of occurrences, and instead of having the intensity, we have the value of the state. Binary images, 1 bit per pixel, 4 states. And that, of course, comes from level 1 K-maps. You've seen it before, 2 variables, 4 states in binary. And of course, I don't have to tell you, they are 0, 0, 0, 1, 1, 1, 1, 0, or in pure binary, 0, 0, 0, 1, 1, 0, 1, 1. And as we increase that operator, of course, the number of states will increase exponentially. A 3-pixel operator would have 8 states. A 10-pixel operator would have 1,000 states, 1,024. So the operator scans the image, and let's take these 2 images here. So the operator sitting on the first image is going to be sitting there. It is seeing 0, 1. Now, with small images, you can slide the operator over row by row. With megapixel images, maybe you just over adjacent positions. So if I'm sliding, I'm going to get it on the left-hand side, the middle, and the right-hand side. If I was just taking contiguous samples, it will be the left-hand side too, then the right-hand side too. I'm going to slide it, so as we go through that image, the top left-hand one with the operator, how many states of 0, 0 am I going to get? 0. How many states of 0, 1 am I going to get? 1, 2, 3, 4, 5, 6. Yes?
Yeah.
So there's numbers on here. 1, 2, 3, 4, 5, 6. So we are going to get an entry there. Of 6. Right, how many states of 0, 1? 1, 0. Next one. 1, 2, 3, 4, 5, 6. Indeed, 6 more. And so we've got noughts there, we've got naught there, we've got that. That is the texture coherence spectrum. And from that, I can get a vector which represents that spectrum. It is going to be a 4-element vector. These are the elements. This is the magnitude. And that will give me a vector representing that texture of x equals 0, 6, 6, 0. Right. Now apply the operator to the second texture. How many noughts in the second texture?
4.
So this is from this one. This is going to be 1, 2, 3, 4, 5, 6. 0, 0, 0, 1, 1, 0, and 1, 1. And we're going to get 4. Just check. 1, 2, 3, 4, yes. We're going to get 1, 2, 3, 4 at 0, 0. How many 0, 1s? 4. How many 1 noughts?
0.
0. How many 1 1s?
4.
4. So it looks like the vector from that texture is going to be, let's call this y, call that x, call that y. There is x. Y is going to be a vector, 4-element vector, which is going to be 4, 4, 0, 4. Right. Let's take another texture. And in terms of texture appearance, this is going to be Z. And let's have these are dots. Now, as a human, I've told you that is class 1. I've told you that is class 2. What do you think the new pattern is? Is it class 1 or is it class 2 in appearance?
Class 2.
Must be class 2. It's a very low frequency. It's okay, it's rotated. It's a big block of black with a big block of white. Right. The texture coherence spectrum for that is a simple example. Can I write it down without going through the graph? How many noughts?
6.
6. How many 0 1s? 0. How many 1 noughts? 0. How many 1 1s?
6.
6. So there I've got the vector for Z. Right, so I've converted the textures to a sort of fixed format. It doesn't matter if the texture changes, the operators are extracting that feature of the texture for whatever occurs in the image. So I've got a vector for class X, a vector for class Y, and a vector for class Z, the test pattern. How do I classify them? What technique that you've already seen would be a good technique to use? Oh dear, you haven't done much revision yet. Term 1 stuff. Vectors are points in multi-dimensional space. These are points in 4-dimensional space. We know 2 points are 2 particular classes. We've got another point in 4-dimensional space. We want to see whether it is the first class or the second class. What do I use? Let me give you a clue.
On the distance.
Distance! Boom, boom. So we can now use Euclidean distance. Right. And for 4-dimensional space, Euclidean distance, this is revision. dE, if this is x and y, it is going to be equal to the summation I equals 1, in this case to 4, because 4 dimensions, of, let's have it between x and z. It is going to be xi minus zi squared. And the whole thing is square rooted if you want. So that is one distance measure we can use. So let's put the patterns on a separate page. So we've got x was equal to 0, 6, 6, 0. Y was 4, 4, 0, 4. And the test pattern Z was equal to 6, 0, 0, 6. Right, so I want the Euclidean distance between x and z. So d xz is going to be 0 minus 6 is minus 6 squared, plus 6 minus 0 is 6 squared, plus 6 minus 0 is 6 squared, plus 0 minus 6 is going to be 6 squared as well. 6 squared is 36, I've got 4 of them, 36, 72. It is going to be 144, and it's square rooted. It's going to be a distance of 12. Agreed? Anybody lost on that one? It might be an exam question. Distance classifiers. Oh, a bit of dirt on my eyes hurting. Right. dyz, the unknown from the other pattern, is going to be xyz. It's going to be 4 minus 6 is going to be minus 2 squared is 4, plus 4 minus 0 is 4 squared is 16, and 4 is 20. 0 to 0 is going to be nothing, 20, and 4 minus 6 is minus 2 squared is 4. It is going to be 24. Square root. And square root of 24, damn it, is nearly 5. So according to the distance classifier, Z is which class? Y. Does it make sense? Go back to the images. That was the unknown. We're comparing it with that one. No, nothing like it. We're comparing it with that one. Subjectively, yes, it's bringing the two together. So that's using a very simple window operator which extracts global features from the image to get a representation of the texture, which you can classify using distance. And of course, if I didn't want to use Euclidean distance, what other distance could I use? If these were 1,000 element vectors, something faster. The square distance or the city block distance. Okay, let's do the city block. The city block is DCB, is going to be the sum of the mod of for xz. It's going to be xi minus zi, I equals 1 to 4. In other words, it's going to be the sum of the difference, the modulus of the differences. So xz, using that formula, is going to be 0 minus 6, and the mod of that is going to be 6, plus 6 minus 0 is 6. They're all going to be 6. I think it is going to be 24. Now dyz, again, just looking at the data, the mod of the difference, the sum of the mod of the difference of yz is going to be 4 minus 6 is minus 2, which is 2, plus 4 plus 0 plus 2, I think it's 8. Minimum distance, it classifies city block as well. And of course, you could use the square distance as well. So there's a little bit of a reminder of city block distances on a new application. Now, if I hadn't got this operator, what would be the alternative approach to textures? Textures are frequency dependent. You want to analyze frequency of an image. Is there a mathematical process that you immediately associate with frequency? If I want to get the harmonics from a piece of complex sound. Hello! It has a spectrum. What is that spectrum? The next word. F. Fourier. So the alternative would be to use Fourier analysis. Now that's heavy mathematics for a single dimensional function, such as voltage time representing speech. When you've got two-dimensional pictures, 16 million parameters, it's going to take a lot of computation. But let's just look at what we might do with Fourier analysis. This is just for information, so it won't be in the exam. These are only maybe a cursory impression. Those are some typical two-dimensional Fourier transform pairs of images. And the image is drawn as a three-dimensional plot. In fact, what those inputs are, this top one is essentially, looking down from the top, it is a square. Actually, the square would be white, so that would be the image looking down from the top. So this is my X, this is my X, this is my Y, and coming out of there is the intensity. That gives a two-dimensional Fourier transform of another image, which is complex, but it has reproducible characteristics. All squares will give that similar type of Fourier transform. This is a circle, and this is a ring. And they are, I'd say, more complex than the original images. Doesn't look good. That's for artificial images, shapes. If we now apply it to pictures, the Fourier transform gets even more confusing. And this is an example where Fourier transform is being used to clean up an image. And if you look closely at this image, it has a lot of dotted distortion there. The Fourier transform of a natural image is this here. And just to explain, what we've got in the center is the DC, or the area of the image that doesn't change with no frequency. And as we move out from the center, we're getting a measure of the higher frequencies in the image. And also as we go around, there's a phase factor. Now this sort of cross-hatching in here is actually these minor starbursts there. And if you get into the Fourier domain, you can play around with this. And if you look very carefully, you'll see on this image, certain areas which correspond to these four features have been blacked out. There's a black window there, there's a black window there, a black window there, and a black window there. Can you see those? So, it's got good eyesight. Can you see that black window there?
Yeah.
Just about there. Where's the other one? Down there, down there. They exist if you can't see it on the resolution there. Now what we've done is we have blacked out those regions. In other words, we remove the frequencies corresponding to these starbursts. And they correspond to the distortion on this image. And when we, having removed those areas, it's changing the Fourier spectrum, it's taking the values down to 0 because they're black in those windows. When we do the inverse transform, we get back and the distortion has been removed. So supposedly after a heck of a lot of processing, we've got a little bit better image. So I don't think that's the way forward for real-time texture recognition. But just in passing, this does have some other advantages. Again, yeah?
Is there a reason why they've appeared to zoomed in as well?
Zoomed in.
If you look at the Fourier space before and after, in the after picture, the ones in the axes go all the way to the edge of the image.
Yeah, I think that they've, yes, they have. There's more going on. It's not my work, so I don't exactly know what's happening. But yes, it does look as if there's more activity there. Yeah, skip over that one. I don't know the answer to that. Right, there's another little thing which might be valuable. I'm sure somebody else has done it. I've taken that photograph and I want that to be a non-fungible token or whatever the latest jargon is on ownership. And I want to be able to identify that as my picture. And when we go to court and there's millions of pounds at stake, I want to prove that that's my picture. So what I've done, however you'll do, see that there? I have added TJS. If you all see it, I've fiddled around with this image and I've put my signature, TJS, in there. In other words, I've removed to 0 certain frequency components. Now, it hasn't been done, but if that was then transferred back to the real image, that TJS would be distributed over the whole image. It would change the frequencies of the whole picture. You wouldn't see the characters TJS, but it would be hidden there in the same way as this distortion effect is based on those 4 areas that I've removed. So I've watermarked or signed the image. And in the reverse Fourier transform, there's no way of telling where that is. So it goes to court. It's my image. No, it isn't. I do a 2D Fourier transform on that image, and what comes back is there. Look, there's my signature. So that's an interesting idea of watermarking images. Might be useful. Might be more useful in the future as images become more expensive and personal property. So that's just a brief introduction to the alternative to texture recognition, which really hasn't taken off in pattern recognition so far because of the sheer processing time. Okay. An example for you guys in your own time. Oh, my pens disappear. repeat the example. A different window, and the window I want you to use is a diagonal window. So that would be your scanning operation, and see what sort of results you get from that. I haven't done it, so I don't know what the results are. It should still work. Now this is a tiny image, a tiny window. And the sort of textures one might use for classification are textures that might look like that. These are from a library of standard textures which are open source. This is clearly a metal mesh. I think this is a stone surface. That's obviously, is it brickwork or it's another metal mesh? Clearly distinguishable from each other, but difficult to define. And if you apply this texture co-occurrence spectrum, and in this case we've got to have a bigger window, so the window I'm going to use for these is going to be a window which centers on pixel Pij, and it's going to be one above, one below side, and t'other side. Let's call those A, B, C, D. So that would be a 4-pixel operator. The Pij just locates it. And if we have 4 pixels and the image is binary, how many states? Oh, come on, level 1, please. N inputs, how many states? 2 to the n. How many functions? 2 to the n. 16. And if you apply that technique to these images, just to show that it does work on much more complicated data, those are plots of the texture code spectrum. State 0, 0, 0, 0 to 1, 1, 1, 1, and these are the numbers there. And if you look at those for those textures, they do look similar. Perceptually, they're similar. I suspect if I took this one, if I compare it to this one, yes, the shape is very similar. This one, no, not like it at all. They are distinct. And the distance classifier will sort them out. Taking the first one as the reference, the other one as new examples of texture, and classifying it. So, it's showing progress. Right. We're working on binary images. The pixels now are 0 and 1. Sounds simple, but you try and get a good texture image by a global threshold. The lighting changes, half the image is going to white out, half the image is going to black out. You're not going to maintain the texture with a single or even an adaptable threshold. It is tricky. We need more resolution at the pixel level. So, for grey level images, right. Let's take part of a real image. There's the center pixels in the center there. Here I'm extracting either horizontal, vertical, or diagonal samples. So imagine those as 1, 2, 3, 4, 5. 1, 2, 3, 3. Yeah, 3, 4. Yeah, 1 is right. The vertical, the horizontal, that diagonal, and that diagonal. 4 different samples. And supposing they were extracting pixels of grey intensity, 8 bits, 122, 95, 104, and 86. Now, how do we get the state of variable pixels? Looks as if we're representing individual values, there's going to be a massive amount of possible conditions. In fact, there's going to be 256 conditions for that, 256 for that, and other. I think it's going to be 256 to the power 4, which is going to be a pretty big number. Solution. Use ranking. And if I label these pixels, oh, it's not allowed. Let's do it on separate paper. Let's take an image. Let's have 4 by 4. I'll do it for 15 bits. 1, 3, 4, 5, 2, 6, 3, 7, 12, 14, 15, 8, 9, 10, 2, 3. Values don't matter. Imagine the operator is sitting here. I'm extracting that pixel, that pixel, that pixel, and that pixel. Let's call these pixels A, B, C, and D. A, B, C, and D. And the values are A is 3, B is 15, C is 12, and D is 2. Having got those pixels, rank them. Brightest to darkest. It is going to be B is 15, which is greater than C, which is 12, which is greater than A, which is 3, which is greater than D, which is 2. And that will be a rank. And from that rank, you can give it a label, and it becomes a state. Right. Now, the beauty of this is, if I change the lighting, or make it darker, if this becomes 1, 13, 10, and 0, I've effectively changed the illumination. The rank remains the same. B is greater than C, is greater than A, is greater than D. So this will be independent of intensity and illumination. So if we have a 4-pixel operator and we're looking at the rank of the pixels, the next question is, how many ranks? For 4 pixels, how many pixels could be the brightest for 4 pixels? 4. How many pixels could be the second brightest?
4. No, 3.
3. How many could be the third brightest?
2.
And you're left with 1. So the number of ranks for 4 pixels it is 4 factorial, because they're independent, and 4 factorial is a nice manageable number. It is 4 times 3 times 2 times 1, which is equal to 24, I think. So your histogram, your Coco spectrum, will now have 24 states with this 4-pixel ranking operator. And you get the same process, having ranked the images, we get the populations for each rank, and again that gives the vector, and we can use that for a distance classifier. Now, if I expand this to, say, 8 pixels, 1, 2, 3, 4, 5, 6, 7, 8, it became a 3 by 3 square, ignoring the center. Then the number of ranks for an 8 pixel operator would be 8 factorial. And 8 factorial is 720, is it? It's getting larger, but it's manageable. So we don't get too much overhead as we increase end, but the 4 pixel operator is still pretty powerful. So that is a ranking operator. It allows us to now process gray textures or color planes, color textures. Color is just 3 gray pictures, which we call red, green, and blue. And how well does it work? Well, the best result that I have seen, I'll give some examples of this. Which one do I want? Yeah, start off with this one. There is an example, getting a bit smeared, but there is an example of 3 textures. One is an artificial weave pattern. This is water, and this is gravel. And what we do is we start a window extracting the texture from a window. That becomes your reference. You move to another area of the region, and if the texture distance is small, set threshold, it's assumed to be the same texture. When we move to a different region, we create a second reference for a second texture, and it becomes self-organizing in finding the different textures. What is the result? Well, from that, these are the different homogeneous regions we have picked out. It's picking out different regions in the water, which I suppose might correspond to different shadings here. This is interesting. The artificial texture, it was horizontal textures that direction, and textures that direction. It picks them out. Donk, donk, donk. So it's looking good. Right, have I got? That's that one. I haven't brought the ones. Oh, there's one separating an aerial picture. Oh, stop it, you things. What university devised such a stupid desk that slips down? They tell me they gave everybody magnets, but they've all been nicked by the students. Magnets to stick on here. Is that true? Right. There's an aerial photograph of the road there. I want to separate the road area from the non-road. It comes out. And the one I think is really fantastic, which is this one. Right. Now that is grass. And what we did, these PhD students worked out did, he took a section out of the center of that image and he rotated it 90 degrees. And if you look very, very carefully, you can see in here there is a region there, down there, down there, down there, and down there, that looks slightly different. You can sort of perceive a difference, but it's difficult to describe. So what do? We train on the outer texture, which is the normal grass. And when we apply the classification window scanning it, that's what comes out. Now it's not perfect, but there you can see the square is slightly different texture. And if you try and use a Sobel edge detector to get that edge, or anything, even a human being, it won't work as well as that. So that is quite a good result on texture recognition. But it is a tricky problem. And we as humans, we recognize most textures just like that. How do we do it? Well, That's the big question on most of this AI stuff. Okay, it's end of the first hour, 10-minute break. One more topic to discuss.
Almost done.
I'll just conclude the level.
Yeah. Do you want a coffee, sir?
Oh, I'll give you an extra few marks. Yes, please.
What do you
Well,
like?
if you do that, I'll buy you a
Warm and
coffee.
wet, milk and 1 sugar.
Just like a normal
Normal, absolutely normal.
coffee.
Yes, Phil filter or Americano or whatever. Yeah.
Yeah, let's go.
Outline. Oh, look at this
Yeah. The one on the left.
on the left.
No, my left. Sorry.
Yes.
And then,
Gosh.
I wasn't sure if we put sugar in it.
Oh, have you? I'll have to buy you one next time because I'm cashless at the moment.
No, that's fine. Don't worry.
Just put your name on the exam sheet. Right, folks, one last challenge, and it's a big one. And we can have some window on how to solve it. And we're going to use techniques we've already covered, so it can be a bit of revision for you as well. Content-based retrieval. Indexing images and pictures with other pictures. You have the option on Google, you can search on images, and it's supposed to bring you images which are similar to the target image. The key is you are indexing by the content of the image, not by any number or reference or verbal description. And where is this used more seriously? Certainly criminal records. The law department have, not the department, but the police and the authorities have large databases of photographs, especially from passports. And you're doing a bit of mischief and get your picture placed, caught on camera, an image of you. First question they ask is this person known to us? Is he or she on the database? And all you've got is the picture. Because if you're doing a little bit of mugging or whatever, it's not advisable to put your name on your forehead. Just got the image. You're setting up a company and you want a trademark. So you get a graphic designer, perfect, wonderful logo. The question is, first asked is this a unique logo for your product? Or has somebody else used it before? So you've created it, so you can put a name on it, but the name is meaningless because it won't be on the name of an existing trademark. Again, you want the ability to say, is this trademark unique or has it been used before? We want to index a database of trademarks with the image that you've created. And it's tricky. So how do we do it? How can we attempt to do it? Well, there's broadly 4 methods. And this work goes back, I guess, about 20 years. One of the pioneers was the old IBM firm. And I was working with them in California in the early noughties when you were kids. And they were trying to look at methods of extracting information. Again, where you might want to use it. You've got hundreds and thousands of photographs on your phone these days. And you go home at the end of term and you want to share some with your parents. This is what Brunel is like, and this is the good things I did. But I suspect you don't want to share all your photographs with your parents. How can you create a system which would pick out the nice picnics in the campus and whatever, as opposed to the end of the evening in the nightclub photographs? Again, there's another application. So basically there are 4 methods. One is color. The second is shape. The third metric is texture. And the 4th method is sketch. Right, well, colour is the most successful. How can we search a database on colour? Well, take the colour image. From the colour image, it is possible to get a histogram. And the histogram would be a record of the number of pixels in each and every colour. How many colours, how many different colours are there in a standard computer image? Pixel.
RGB.
They're types. 16 million colours. So if I were trying to get the histogram on the number of pixels of each possible colour, we would have a histogram which would go from 0 to 16 times 10 to the 6 approximately. And how many pixels do you have in a high resolution image these days? About 16 million, 4,000 by 4,000. So what we would have here would be an extremely sparse histogram. We've got 16 million buckets, and we've got 16 million objects to fill in those buckets. Chances are, if it was evenly distributed, you'd only have 1 or 2 in each bucket, and some wouldn't have any. So the resolution actually is too high. So we can't take the total image. If we can't take the total image, use the color planes. And that will give us a histogram. And this would be number. And for the red plane, it will be the first 8 bits of the 24 bits per pixel number. And the red intensity can range from no red at all, which will be 0, to maximum red, which will be 255. So we would need 256 entries. And that would be the red spectrum. Add to that the green, which would go from 256, add another 256, I think is 512. And add to that the blue, which will take us, I think, to 758, which is a manageable size histogram for distance classifier. We've got 16 million possibilities, so we will get repeating color content. Right, so the red might look something like this. The green might look something like this. And the blue could be, again, something like that. We've got our histogram. 756 or 58 element vector, distance classifier. Known images in the database, got the color histogram. Your unknown picture comes along, calculate the color histogram, do a distance classifier of your histogram from the ones that are stored in the database. Find the one with the closest distance. Sounds good. It is plausible, but there is a problem, folks. And it's all to do with the nature of colour. And there's the colour wheel, which I'm sure you've seen before. Red and green and blue are the principal colours. Yellow exists, but it doesn't exist. Yellow is perceived by us, but what is yellow? It is green plus red. And this is cyan, or whatever, the cyan there, which is red plus blue, and we have colour mixing. Now, if I were trying to do a search on images, and let's create some very simple images. Where are they? Let's have an image which is red and green. Okay, can you imagine that? Okay, it's sunset in the countryside in a field, if you like. But I've just put it as a red block at the top and a green block at the bottom. And I've got another image which is again divided into two, yellow and black, which a red and green image and a yellow and black, they're miles apart. You couldn't see any as a human, any similarity between them. Yeah? If you like, this yellow is, I don't know, it's a tiger at midnight or something like that. But we've got just simply two blocks of colour. Now, if I were to get the histograms of this one, let's call this 1, call this 2, the histogram of 1 and let's assume these colours are maxed out. It's maximum red, it's maximum green, it's maximum yellow. So no shades, it's the brightest they can be. Now on the red plane, this image, half the red pixels are going to be at maximum value. So if the red is 0 to 255, and this is 50%, 100% total. The top half of pixels, the first 8 bits of those pixels, the red plane, is going to be maximum red. And so we're going to get 50% of the images at maximum red. There, from there. What is the red content in the green half of the image? Red content in the green half? None. So the intensity of the red part of the red plane in the green image is going to be 50% of the pixels at 0. Right, now we go for the green plane. And let's do that. I'll do 0 to 255 for the green. We have to add them together, of course, for the vector. And for the green plane, the bottom half, 50% of the pixels will be maxed out. So there would be my 50% there. And there's no green in the red plane, so the green content will be all zeros. So we'll have 50% at 0 there. It will look like that. And now we go to the blue plane. How much blue in the red and green image? None. So we will have 100% of the pixels at 0. So that would be the histogram for the red and green image. Okay, it's very simplified. I just want to demonstrate a flaw in the system. Of course, in real life, we wouldn't have maxed out colors. It wouldn't be silly artificial images like this. But the interesting thing is, let us now get the histogram for 2. This is histogram for 1, the histogram for 2. Yellow and black. Again, we want R, G, and B. Right, the yellow half, the 50% of the pixels that are yellow. Let's put that back to give you a clue. Where's it gone? Let's put it up there. Right, the amount of red in the yellow plane, 50% of the pixels will be max red. Yes? Naught to 255. And in the bottom half, the black, the red portion of the black pixels will be maxed down at 0. 50% will be 0. Now for the green, it's going to be exactly the same because yellow is green and red. So we will have 50% for the green at 0 and 50% at max. And the amount of blue in these, 100%. We get exactly the same histogram because of the nature of color and the fact that colors, apart from the 3 primary ones, are mixtures and additions of the other. So there we are. You're looking at a set of, you want to retrieve images of, I don't know, ancient buildings in Egypt, sandstone colored, and that's your target image. You've got a whole database of Google. You put in the finding images of these buff colored buildings, and what comes out is occasionally in the list a beach scene. Why? Same color. So we have a problem there, and if you do colors, if you do searching for images on content, some of the results, most of the results are quite impressive. You get 30 pictures. Most of them are recognizing conceptually similar to your test one. But the odd row comes up. You say, why on earth is it doing that? It's due to this color matching problem. So that is not a perfect method, but it is better than some. Now the texture searching. That was the second one I was doing, wasn't it, on my list? No, the second one was shape, I think. Shape, sorry. Now this is mainly for artificial images, industrial images and whatever. We want to look at the images with squares in them and triangles and circles. Find me an image that has squares, circles and triangles in it. Well, the first thing to do is to segment the image. To get the individual shapes. So we would get the square, the triangle and the circle, or any other shapes in there. Right, the histogram we need is going to be the number as usual. And what we are going to plot here, can anybody think of a metric that is shape related? Lecture 2. Shape factor! All right. And what is the shape factor? The equation of the shape factor, my friend.
Yeah, yeah, the dimensions.
Area, I like the sound of area. What's the other one? Perimeter. And so what is the equation?
Yeah, yeah, the dimensions.
Is it perimeter squared?
Perimeter,
Yeah.
perimeter squared divided by area. So S is equal to P squared over R, over A, sorry. You get the area by counting the pixels that are in the image. The shape factor, you've got the edge detecting algorithm, you get the edge of the shape. You can count the pixels in the edged shape, and that will give you your perimeter. And the minimum shape factor is what? What shape? Most compact shape? Circle. And what is its shape factor? Well, if you can't remember, plug it in the equation. For a circle, S is going to be P squared over A, which is going to be 2 pi R all squared over A, which is pi R squared, which simplifies to 4 pi. But, that's going to be, let's put in 4 pi squared R squared divided by pi R squared. The R's go, one of the pi's go 4 pi. And 4 pi is equal to about 13 approximately. But I don't want to start the shape factor from 13, I want to start it from 1. So in this case, you would use the normalized shape factor, and the normalized shape factor is the shape factor divided by 4 pi, which reduces the most compact shape down to 1. Don't have to do that, you can start at 13, but it's a bit unusual for a vector to start at element 13. So, having got that, you get the distribution of the number of shapes. The number of circles will be there. Then we have the number of squares, triangles, squares, oblongs. We might get something like this. We'll distribute the shape factor going from 1 up to 2, 3, 4. Again, it's a histogram. So that then becomes a vector. You've got the images you're referring to. They have also got their shape distribution. And you can search again using distance classification on that. So that is shape. Texture is quite useful. Let's get myself sorted out. And that one. Always have a coffee, yes. Oh, delicious. I must remind you, drinking and eating is not allowed in the lecture theatres. Get out of the side of camera, yes. Right. Where's my slide I showed you in the first half? Yes, here it is. Get some textures. These were for the 4-bit operators, so the number of states we had was 16 for binary textures. If we're using the ranking operator to define the states, there will be 24 possibilities. And they are converted to vectors. The vectors would be, these are different examples of the same texture, not exactly the same, but similar. So we would store the images. I've got this histogram here. I want to find out how the distance is from the first one, second, third, fourth, and 5, and so on. How does it work out? Well, these are some real results. Again, it came from a PhD student. Stay put. This is the database. Well, these are taken from the database. This is the target query. I want to find images in the database that look like that image. Now, I'm just using the image. No tag, no name, no description, just the pixel values. And using the texture cocurrent spectrum, searching in the database, this one comes out as being similar to that. Not the same, but similar. And I reckon that's pretty good. As we go further away, that comes out, that comes out, that comes out, that, and then it starts to lose its similarity. I reckon that's not a bad retrieval. Taking a much more random texture, there is the query, there's the best match, there's the next best match, and so on. So it is starting to do something which is perceptual, and you're retrieving without any index, without any keyword, without any description whatsoever. Just the content as the means of detecting. Now, the final one, which I think IBM was having a bad day when they suggested this, was retrieval by sketch. I won't really say too much about this. And the idea is you want to retrieve an image, you get an accomplished artist or somebody to draw witness to the crime. Oh yes, I remember the guy, I can draw the face. And you want somebody to draw the face, there it is. This is definitely the guy who did it. Now that seems totally implausible that you can take any information from that sketch and match it with real images. But have you ever looked at a cartoon? A cartoon is a line sketch. It's a hugely distorted line sketch. But it's obvious that the person is, I don't know, the Prime Minister or Putin or whatever. And we as humans can actually do it. So there is a link there. And this was used in one application I know was in the university in California, where they had an art library and people wanted to access material which was archived. And, you know, again, is there anything like my drawing? And they got about 10% reasonable results, which is not a solution to the problem. But it was better than nothing, because without that automated system, the only way you could go to that archive and get anything like what you wanted was talking to the person who was in charge and saying, I want this picture, it's a picture of a tree or a sunflower with in a vase with whatever. And you were relying on his or her knowledge of the database. So it was starting to automate that human process. So when you look for pictures like this on your phones or on Google, it's a tricky problem. If you get strange results, you might, not good, it's not working perfectly, but you might understand, certainly on the color, why it's happening. But remember, humans are pretty good at it, so there is a solution. So that really is about all I want to say. I was going to talk about smell detection, but I don't think it will be an exam, but it's another interesting, just very quickly, just interesting. Don't take any notes on this one. How do you make a smell camera? A camera for smells. You take a simple transistor amplifier, RL and R. There's a simple transistor. Remember a circuit like that? You put the signal in here. The voltage there will bias the transistor and cause an output voltage, either bigger or whatever. Right. What happens if I put an organic compound on this resistor that looks like a capacitor? And it has the ability to absorb gases, and it will change the value of the impedance. Typical of what you get with gas sensors. They absorb the impedance of the material changes and you get alarm signal. So what you do is you impose a organic compound on that, and it will respond to the gas it absorbs. Now, a single gas detector will just be targeted at carbon dioxide, sulfur dioxide, or whatever. Suppose we took an array of those cells, each with a different polymer overlaying the input resistance, each targeted at a different gas. We would get a series of voltages, which could be displayed as intensities, which would be a picture of the range of smells that are coming in. And here's an example. There's the idea of capacitors with these polymers, each one being different, on top of changing the impedance. So what happens? We put them, expose them to different compounds, and even though the polymer might be targeted at acetone, the other polymers will absorb to a certain extent, and we will get a profile. Put in a different one, benzene, put in chloroform, something different comes out. And now we've got those histograms. From them, we've got intensity vertical, and we've got, just label them 1, 2, 3, 4, 5, 6, 7 in the order of the compounds they're targeted at, and keep it the same format. You've got a vector again. So this would produce a vector, which might well be, I don't know, 10, 3, 4, 2, 9, 8, 5, 6. And that would be your vector, your point in space for that particular compound. Test it on an unknown compound, distance between this, this, and this, and you've got a smell detector. Now, certainly it has applications for explosives and whatever, but I spent a bit of time at Caltech many years ago. One of my good PhD students became a professor at Caltech, and he owed me a favour, a cup of coffee. Yeah, he invited me to Caltech, and we were working on this, and we weren't applying it to explosives, we were applying it to personal identification. It gets a little bit, yes, interesting. Now, the idea is, without being too indiscreet, you can usually recognize your own atmosphere. You know, the clothes, oh yes, that'll do another day. And I suspect, I suspect if you all took your socks off and laid them out here and did a sniff test, you just might be able to recognize your own from other people's, because normally one's own atmosphere and environment is acceptable. And the idea is that, okay, humans have a whole range of smells which are pretty awful. They're chemicals. It's sulfur dioxide, it's ammonia, it's hydrogen sulfide, that really smelly one. It could be the whole group. And on their own, they smell pretty awful. But there is something else there which is more personal. And these are your own pheromones. And they seem to differ from individual to individual. And if you want any more proof of this, if you have a dog, you leave your coat in my house, I give it to my colleague, and he will track you. and stands a better than zero chance of finding you. So there is something there, but there is a personal identification. So what we were doing, instead of using acetone, benzene and chloroform, we were using these smell sensors under my arm, under your arm, and so on, and getting the references, and then testing on different examples, and it worked. Only trouble with this is, unlike cameras, ordinary visual cameras, these devices are absorbing the gases. And if these were photocells, you could change the light on them and the response would change in nanoseconds. Because there's a physical absorption of gases here, it takes time, having used the damn thing, for it to purge, get rid of the previous smell, and be ready to start again. So they tend to be pretty slow in operation. You might have to wait 5 minutes between using one and another and testing it again. But it shows potential. So I was going to talk about that. Again, it was a PhD student some years ago. This was more for military applications. Where's the slide? He built a tracking device. Basically, it's a little mobile robot with 1, 2, 3, 4 sensors. He had a reference there. He'd take another spectrum there, histogram there, another histogram there, another histogram there. If you know what your target is, taking which histogram is close to the target. Supposing we were using isopropyl alcohol as a target, and we knew what the target was, we were getting the histograms from these three, which is the closest, move in that direction, and the thing would move and track. And that was an interesting little experiment. Right, but I won't talk about smell in the exam at all. I'll leave you to deal with your own smells in the exam. Okay, closing comments. AI. Lots of promise. Most probably your careers will be involved in AI to a certain amount, a certain extent. Lots of promise. We still really don't understand what's going on. It's tantalizing because we've got human activity, which is proof that data can be processed. A lot of people who use AI systems will just download a software system and throw data at it. And they haven't got a clue what's going on. So although some of the stuff I've talked to you about is a bit tedious, I hope you've got an idea of what the hardware has to be, what the limitations are. Because I've talked to people in the past, system doesn't work, I'll train it more, I'll train it more. It needs more training. No, if the system can't support the function you're trying to implement, it never will work. The exclusive OR function with the analog neuron. You can train it till the dogs come home. It will never work because if you then look at the data distribution, if you've got two classes where that is X, that is X, that is Y, and that is Y, and you're looking to put a plane there, you can see it in 2 dimensions. You'll never get a plane that has the 2 X's on one side, a linear plane, and the 2 Y's on the other side. It won't support the function. And of course, that's just 2 dimensions. This problem occurs in 200, 2,000, 2 million dimensions, and it's not easy. What is the key to understanding AI? I guess it's consciousness. And I haven't got time to talk about consciousness, but we all have it. There was a brief lecture, a guy from Stanford talking about AI early part of this year, end of last year, I think it was. And he said that the trouble is we're trying to get consciousness into these machines, and we haven't got a clue what consciousness is, either in a machine or even in a human. And we haven't, because your brain, it's just voltages from the eye, the picture goes in, from the back of the eye to the brain. It is voltages, a few tens of millivolts going into the brain, millions of voltages. how on earth do they become that picture of you that I see? And it's not the moral consciousness I'm talking about, it's the consciousness of just being aware. And really, and we have set up systems, you can put in a, supposing I have a pattern there, let's have a letter T there. I have a neural network there with many, many outputs, not just one, which produces pixels here. So there's a sampling there. These are producing outputs. And each output is a pixel of an image. And I can train some of these, maybe 10,000 neural networks in there. I can train some of the neurons to output a 1 and some of them to output a 0. I can train them, supposing those are all 1s, I can train it to actually output something that looks like a T. Now, that's never going to work perfectly because you never get 100% from a real image. But if it's T-like, what is an interesting experiment is to say, okay, that looks subjectively like a T from a human point of view. Let me put that back into the input again and feed it back. And will it become more T-like or will it not? And you can sort of generate loops of feedback and dynamic loops which will home in on a stable state which is T-like, and another one which could be A-like and B-like. Your face or your face. I'm looking at you, yes, your face. Yes, I remember it. Close your eyes. Yes, gosh, I still remember it. And that's interesting, but it doesn't really give us a full explanation. And of course, the other thing is, dreams. What's a dream? If you're having this model with feedback, let's have a random feedback. Start off with a random picture, outputs 1, another one. And is that a possible model of subconscious thinking? They're crazy, but possible. But all we really need to do, at least all Elon Musk wants to do, is detect the edge of the road. People in front. Sounds simple, but it ain't. So, I hope you got to AI. My stuff is one side of it, Tatiana's is another. We're both looking at nature for inspiration. And what we do know is that your brain is electrical. And it's an electrical process. Mechanical engineers ain't going to find out what's going on, that's for certain. So there we are. That's all I want to say. Next week, Tatiana, week after, I'll turn up and we can chat. Bring some problems if you like, and I'll go over them. And we'll let you know a guide for what the exam questions are going to be this year. That doesn't, I must emphasize, if I tell you, or if we tell you, that the main topic of the questions are going to be A and B, it means you should focus on those and expect those. But it doesn't mean to say the rest of the material can be neglected. And if you're planning, because Brunel is such a fantastic place, if you're planning to fail the exams and take the resits, because the resits, more time here, it's going to be more fun. Don't recommend it, by the way. The exam, the resit exam will be different. We will give you different advice on the topics. So nothing is excluded from the exam, but we will give you a guide on what the main focus will be. And the main focus should enable you to get at least 40%, hopefully 70%. Yep.
The marking equal for each question?
Yeah, 25% on each question.
So what about, you said there is 4 questions and you have to answer all of them.
Yeah.
What do you mean by that if you like, for example, do 3 of them?
Oh, you get 75% maximum or 50% maximum.
Oh,
Yeah.
like, just,
Yeah. No, we're not requiring you to submit a perfect solution before we mark it. So you don't have to worry about the choice of questions straight in there. You know what the topics are going to be, then so it's going to be something on image processing, there's going to be something on analog neural networks, there's going to be something on digital neural networks, classifiers. Get familiar, understand the basic topics, and then you can express opinions on the rest. And those opinions and explanations, I mean, it's a research topic, so you come up with a brilliant idea, and I just say, bloody hell, this could be right. It's not an exam question, the answer, but wow. Understand, don't rely on memory, just don't rely on memory. That's it, go on, finish my coffee now.
Behind on the nights, I think. When I handed in my last assignment Monday,
Oh, you're going to,
I'm actually
I'm gonna go